Welcome everyone to another OCP Tap call. This is call number 117. Today we have Dr. Jonathan Roseland. Dr. Jonathan Roseland has an extensive background in ultra-fast atomic and quantum optics, along with 20 years of experience toward developing ultra-fast laser systems. Dr. Roseland co-designed the vector atomic ASICs, optical iodine system, and the EPIC and music frequency combs. He has been a principal investigator for several governmental programs, including the AF-CPAC Phase 2 SBIR optical chain front end for lattice clocks, which delivers a 3U Hertz level 1556 nanometer laser system, accompanying stabilized fiber frequency comb, linking the rubidium wavelength to the strontium wavelength at the 689 and 698 nanometer. Dr. Roseland completed his PhD at Princeton University studying the interaction of shaped ultra-fast laser pulses with atomic and molecular systems. He has been a Marie Curie Fellow at the Laboratory Kastler Brussels in Paris, where he created entangled frequency combs to be used for precision metrology and quantum information. So today's talk is about picosystem optical timing networks. And with no further ado, Jonathan, the floor is yours.
Okay, great. Well, thank you very much. Thank you for the kind introduction. Good afternoon, everybody. So as we just heard, my name is Jonathan Roseland, and I'm very happy to be here today and speak about some of the timekeeping work that we've been doing at Vector Atomic over the last several years. Specifically, I want to talk about using optical clocks and time transfer techniques to set up and synchronize timing networks with picosecond precision. So we'll start by just giving a quick, I'm sorry, I'm looking at the wrong slide here. Okay, a quick overview of the talk. So Vector Atomic has been developing optical timing hardware over the last several years. And so we're excited to say that we now have two commercial products in this field. So our clock, which is the EG30, as well as a dual frequency comb. So my colleague, Marty Boyd, he gave a nice OCP TAP talk this past April. So this focused on the clock hardware and really showed the potential capability that a portable optical clock brought to the table. So we also had a publication this year that discusses a lot of the technical details of the clock. So if you're interested in the nitty-gritty of how these things work, I would refer you to Marty's past talk and this manuscript. So today I just want to highlight some of the recent demos that we've been doing toward the goal of getting this optical clock work out and into the world. And after that, the bulk of the talk is going to be about the other side of the coin. So we've got these clocks, and so now how do we synchronize these distributed optical assets? So as a company, we've been working with the team at NIST Boulder in building hardware for actualizing two-way time transfer. So again, Emily Caldwell from that group, she gave a really nice talk this past September, where she really drilled down and reviewed all of the principles and applications in using frequency combs for time transfer. So today I'm going to focus a lot on the hardware side of things, what we've been developing at Vector Atomic to support this collaboration, and then as an example, to talk about a recent demonstration that we did at NIST this past spring in creating a 3-node optical timing network. And then finally, I'll close out the talk by discussing yet another approach to optical time transfer that we've been building up at Vector Atomic, where we replace the frequency combs with CW lasers and integrated photonics. Okay, my apologies. There's there's a lag here. Okay, there we go. So Vector Atomic is a small company. We were founded in 2018, and we're proud that actually just this past week we added our 59th employee. So we're located in Pleasanton, California. So this is the San Francisco Bay Area, and we've funded and bootstrapped our way up through competitive government R&D contracts. And over the last several years, we've focused on fielding pre-production units, and several of these units, specifically in the timekeeping arena, are now transitioning to commercial offerings. And so this is a photograph of some of the hardware that we've built here. So there are the optical clocks, these synchronization modules. We'll hear about these today. But we've also developed and fielded an atomic gravimeter, as well as an atomic gyroscope. So the clocks and the gravimeter have undergone sea trials, and this gyroscope has actually been delivered for an upcoming space mission. Okay, so as I said, the bulk of the talk today is really going to be about timekeeping. And so we've been building up our timekeeping hardware for the last several years. And this really started in 2018, where we worked hard to validate things at the concept level with lab experiments. And from there, we quickly designed and built up the basic subsystems of our clock, so notably the spectrometer, as well as the frequency comb. These subsystems they came together into the first generation of our clock that we did some initial exciting demos with. And this has now evolved into our first commercial product offering, the Evergreen 30. And so we started manufacturing this at the tail end of last year. And so it's worth noting that all of the core components and subsystems contained within these boxes, they're all designed and built in-house. This allows us to really maintain a tight system integration. And then we're also, in parallel, working on being more and more aggressive with the swap-C of these systems. And we're hard at work in developing a 5-liter version of this Evergreen clock. And so that's currently underway as we speak. And then also we're relaxing the performance specifications a bit and working to get this down to a 1-liter version as well. So in addition to the 3U turnkey clock, we've also developed a dual comb, frequency comb system. I'll say more about this in a bit. But having these portable units has allowed us to take the clocks off-site and participate in a number of really interesting demonstrations. So these clocks have been used as a timescale reference. They've operated on ships. Now we've driven them around in cars. They've served as a frequency reference for quantum computing. They've acted as a flywheel for the generation of low phase noise microwaves. We've done optical time transfer experiments. And then most recently, they've served as a time base for VLBI astronomical experiments. And so I'm just going to focus on 2 of these recent demonstrations today, just to give a little glimpse as to the potential for getting picosecond timing out into the world. So the first of these was to take the clocks on a recent driving campaign. So in 2022, these clocks operated on a ship, but we wanted to actually put them in a more dynamic environment and see how they did in the back of a car. So we loaded 2 of the Evergreen systems in this crate here, and this was placed in the back of a car. And we drove the car from our building in Pleasanton up Mount Diablo. So this is the most prominent peak in the Bay Area. It exhibits a prominence of about 3,500 feet. So in order to get from our building to the top of this mountain, so we had to go over some surface streets as well as a highway going between the 2 towns. And there's a number of bumps in the road that routinely cause a few G shocks. A record of the recorded acceleration profile as the car was zooming down the streets and the highway is shown here. And so what's noteworthy is we don't see any bleed through of these shocks into the frequency record that's measured between these two clocks. This is shown in the upper panel. And so, of course, we can quantify this a bit more carefully, and that's what's captured by this middle plot. This is the short-term Allen deviation, and we see that the clocks are still faithfully performing at about 3 parts in 10 to the 14 at a second and averaging down. This is roughly the same level of instability that we see in the laboratory. So we were pretty excited and encouraged to see that the clocks can continue to provide picosecond level timing, even operating in a mobile platform such as a car. So another interesting opportunity came this past summer, where we had the chance to use our clocks for VLBI, or very long baseline interferometry. So there's a radio telescope at Kitt Peak Observatory. This is just outside Tucson, Arizona. And they are a member of the Event Horizon Telescope Collaboration, or EHT. So EHT is probably most famous for these really stunning radio images of black holes and quasars that they've made. So an example is shown here. And the way in which these experiments work is they typically do measurements in the hundreds of gigahertz type of frequency regime. And the way that these tones are created is to actually multiply up 10 megahertz from their local timescale. And so they utilize the lowest phase noise, best-in-class masers. And so this really requires exceptional phase noise, short-term instability in the range of about 10 milliseconds out to 100 seconds. So beyond 100 seconds, the coherence of these experiments is actually limited by atmospheric effects, and so not by the time scale. So we brought 2 of these evergreen systems to the 12-meter telescope shown here, with the goal of measuring them against their best-in-class maser. That's actually shown in this right-hand photograph. And so we wanted to get a baseline measurement to see how the clocks were doing against this maser. And then if they did not degrade the time scale at all with respect to the maser, there was the potential to actually unplug the maser and plug in one of these evergreen clocks into the telescope time base and actually do the spring 2024 viewing period of the EHT with the evergreen clock. So the results of that initial characterization are shown here. So what we see is the Allen deviation and the phase noise of the 100 and 10 megahertz outputs of the clock, respectively. So the orange curve is a measurement between one of the evergreen clocks and the maser that was at the Kitt Peak site. And then if we just measure 2 of the clocks, one against the other, we see the dark blue curve. So if you can assume that both of these clocks are contributing to this measurement instability equally, so you can divide this by √2, and we can infer that the iodine clock instability is this dotted blue. So we want to compare this dotted blue to the orange, and the increase here is attributed to the maser. And so we see right away that the evergreen iodine clock, it offers a really nice improvement in the short-term performance, exactly in this time window of interest, about 10 milliseconds out to 100 seconds. Similarly, we see a nice improvement in the phase noise, particularly in the high frequency phase noise of the evergreen RF output out to a megahertz. And we were very pleased to see that there was no impact on the short-term instability due to operating these 2 clocks outside the lab environment. So at that point, so they passed the preliminary test. And so the people running the telescope at Kitt Peak, they decided to plug in one of these iodine evergreen clocks into their time base and actually do a viewing period of the entire EHT collaboration using the evergreen as their time base. And so in the spring, in the time period in which the evergreen clock was in Arizona, the EHT was observing this distant quasar. This is about 5 billion light years away. And so during a given viewing period, the telescope was pointed at here. And so a neighboring telescope at Mount Graham, it's about 180 kilometers away, they were also observing this quasar. So at the conclusion of the measurement, each one of these telescopes, they shipped off their data to MIT Haystack, where it was run through the cross correlator. And immediately the people there saw this really strong high SNR coherence peak between the evergreen run observatory at Kitt Peak and the one at Mount Graham. And so it's nicely aligned, that this fringe in frequency and in phase. And so it really confirms, it was a very exciting confirmation of the noise properties of the evergreen iodine clock across, this is from a 4-minute viewing period. So we were pretty excited about the results of that. And so actually we had the opportunity just this past week to participate in another VLBI experiment. This time it's in Hawaii at the Mauna Kea Observatory. And so they're studying astronomical effects at an even higher frequency, now up to 690 gigahertz. And so we brought 2 of the evergreen clocks up to Mauna Kea. This is just shy of 14,000 feet. And they were installed in the SMA basement vault. This is the sub-millimeter telescope array. So 2 of these clocks were installed here, as well as the measurement apparatus to compare against the time base there. So a little snippet of that data is shown here. So we see the decorrelated performance of the 2 evergreen clocks, as well as the time base that the people at Mauna Kea are currently using. They don't presently have access to a Mason. They're using a quartz OCXO. And right away, you see the big win that the evergreen brings to the table. So it's better than the existing timescale over this entire viewing period. So Micah, Parth, and Paul, who did the install for Vector Atomic, they were really excited to see this. And so they got to enjoy a beautiful sunset over the Hawaiian Islands. So both of these demos, they were using the Evergreen 30. So which, as I said, this is our first commercial offering. And so we're pretty excited about this. We've really worked hard over the last several years to get this to the point where it's ready for sale. So it's presently about 10 times smaller than active hydrogen masers, and it offers superior phase noise and short-term instability. So this is a recent measurement between 2 of these evergreen clock systems. And so they are exhibiting short-term instabilities of about 3 parts in 10 to the 14. And they're averaging down to instabilities better than a part in 10 to the 15. And if you actually de-drift the data, so they're actually staying below 10 to the 15 for extended periods of time. And so we found use of these in talking to customers as frequency standards, low phase noise radar, VLBI, and wavelength references. And so we're excited to say that we're now accepting orders for these, and you can check out the data sheet if you're interested at our website. And just to show some of the additional hard work that we've done toward automating the system. So this is a fun time-lapse video of bringing the clock online. So we turn on the clock, and we're using this frequency counter here just to exhibit when the clock is locked up. And so for the first couple of minutes, the automator is turning on the lasers and bringing everything up to temperature. So after a few minutes, it proceeds to locking the internal laser to the iodine molecules. So that happens in pretty short order. You see the optical frequency appear here, indicating that it's locked, at which point the automator transitions to locking the frequency cone, and then you immediately see this pop in on the counter. So this front panel touchscreen, it offers a number of RF tuning options to the user, as well as showing plots and a lot of nice telemetry. So we're pretty excited to to have incorporated this really turnkey feature and to start to get these out into the world and see the exciting things that people are doing with them. Okay, so at this point, I'm going to segue into the second portion of the talk, which is really focused on how to compare or synchronize multiple of these clock assets once they're out in the field. So we can first provide a little bit of motivation. So what's the utility in setting up picosecond timing networks? And so one very obvious one is an improvement in spatial positioning. So if you take a typical timing uncertainty, let's say 10 picoseconds, you multiply this by the speed of light, you see a spatial uncertainty of about 3 millimeters. So to put this in perspective, so current GPS, this offers timing uncertainties of about a nanosecond. This translates into 30 centimeters. And so you see a big bump in improvement in potential spatial positioning. So you can really begin to think about now autonomous car and plane operation. You can also start to think about upgrading the current GPS architecture to a GPS 2.0 that utilizes ground-based master optical clocks, as well as satellite clocks. And to that end, there's a number of companies that are pursuing a goal of centimeter type positioning in setting up alternative PNT satellites in a LEO type of structure. So harkening back to the VLBI experiments, and so there are applications in distributed antenna arrays. So these experiments typically work at hundreds of gigahertz. And so if we take 100 gigahertz as a benchmark, the period for a tone at 100 gigahertz is 10 picoseconds. So if we have multiple installations of these antennas, you basically would want to phase align these. A rule of thumb is, let's say, a tenth of the wavelength. So that would be to within a picosecond. So the optical clocks are able to provide this. So the takeaway here is that transitioning to an optical time base, this provides better, higher resolution pictures. There's very clear applications in the dissemination of time and frequency. So in order to eventually redefine the second, we're going to have to figure out a way for the national metrology institutes throughout the world to communicate their optical timing information to BIPM, so we can all agree upon a centralized timescale. And then, of course, in telecommunications, future deployments of 6G, for example, there's ideas to use improved time bases to increase data rates and knock down errors as well. So we can ask, well, what's the current state of the art in means for achieving time transfer? And so there are a number of really cutting edge microwave-based methodologies. And so two-way satellite time and frequency transfer, or TWIST, and GPS carrier phase. So these two achieve timing resolution about 10 to 100 picoseconds. So this is sort of exemplified by recent design on the ACES mission that achieves instabilities in this ballpark. So you can also attack this with optical techniques. And so the T2L2 laser ranging project, this was on a recent JASON satellite. This received timing precision of about 10 picoseconds. And so, you can ask, is this good enough? And to answer that, we can go back to the TDEV plot for our evergreen clock, or this is the accumulated timing error. And so the evergreen performance is shown by these open green circles on the plot. And so we see at short time scales, the RMS jitter of the clock is about 20 femtoseconds, and it is able to hold a picosecond for time periods up to about 1,000 seconds. So we can say, well, if we want to synchronize multiple of these assets, the timing, the contribution from the synchronization strategy should be about 10 times better, 10 times lower noise than the clocks themselves. And so to get better than picosecond synchronization, we really need to move to optical approaches. And so there's a lot of great ways to do optical synchronization by fiber. we have been interested in the capability to synchronize assets that are not connected by fiber. And so, for example, a ground station to a ship or a moving satellite. And so this really requires free space optical techniques. And so at Vector Atomic, we've been pursuing two approaches toward that goal. So the first is utilizing optical frequency combs. And so this is falling back on this great approach pioneered by the NIST Boulder team. So as I said, Emily Caldwell really gave a fantastic talk about this just this past September, where she really drilled down and talked about all of the principles underlying time transfer using combs. So here's a few references outlining their technique. The important thing to mention is that in this approach, it's the actual frequency comb itself which is transmitted over the air and as a means to disseminate the timing information. So another approach, this is really spearheaded by a team at the University of Western Australia, is to utilize a CW laser. So again, here's a few nice publications detailing the methodology of this. And so the difference is, so rather than transmitting a frequency comb, so they are now sending a CW laser across a free space open air link to carry the timing information. So I'll talk about our efforts on the comb-based approach first. And so this is a snippet from the recent publication. So Emily showed this as well. A recent publication that the NIST group had, where they did this really phenomenal experiment. They had two sites co-located on the big island of Hawaii, Mauna Loa, and they sent frequency comb pulses over 300 kilometers round trip, and they were able to measure femtosecond type of precision difference between these two co-located sites with only picowatts of received power. So this is really great. This is a block diagram showing all of the apparatus that goes into making this work. I'm not going to go through the details. I just put this up to motivate that Vector Atomic effort in this collaboration. We've really been focused on operationalizing the transceivers. So that is shown in this block diagram. So this includes the frequency combs and the means for actually discriminating the timing uncertainty between the local and their seed pulses. So if you were to take a look at the infrastructure that is behind that NIST experiment, so that's exemplified by this photograph here. And so there's a lot of things here. So there's current sources, and there's photodiodes and power supplies, frequency combs. There's fiber components and transceivers and patch cables connecting all of these things. And so we've really been working in this collaboration to develop integrated hardware in order to execute this free space optical two-way time transfer scheme. So to that end, we've improved the integration of all of this hardware and robustness. We've done that by developing these Gen 1 transceivers. They're shown on this photograph. In order to get from this picture to this, we really had to tightly integrate and improve the robustness of our frequency comb, all of the optics in the transceiver, and really to design custom electronics to get all of this into a single 3U rack mount unit. As help in that process, we've leveraged integrated photonics to further shrink and reduce the tempo of the heterodyne optics. So as I said, a big part of this has been to attack the swap of our frequency comb. So when we started our initial frequency comb, it's shown in this left-hand photograph. This was an all-fiber comb. It consumed about 15 watts. We eventually transitioned to incorporating integrated photonics to achieve our self-referencing. And so this Gen 1 comb, so this exhibited a savings in power. We were able to knock it about in half, down to 7 watts. And we're excited to say our current comb, we've really been hard at work, again, attacking the swap. That now consumes only 4 watts and occupies a volume of 0.1 liters. And so this little package that you see here. So in addition to obviously the comb, this includes all of the self-referencing modules. It includes all of the photo detection to actually lock up the self-referencing beat nodes. And this includes the pump diodes as well to actually drive the comb itself. So we're excited by where we've taken this with the frequency combs. And this has allowed us to get aggressive in the integration of these transceivers. So as I showed you before, each one of these 3U boxes, it contains a dual comb system, as well as all of the temperature control, the current sources to drive the laser, and the transceivers. The transceivers themselves rely upon a custom photonic integrated circuit that we developed. So this generates the timing discriminator, as well as all of the relevant servo beat notes. There's 16 fibers coming in and out of this chip that's housed inside of this chassis. And one of these transceiver boxes, this interfaces with the existing free space optical two-way time transfer infrastructure that was built up at NIST, and also interfaces with their signal processing units to translate these optical timing discriminators into actionable electronic signals that are then used to measure time differences between local and remote sites. So as I said, this is all done in collaboration with Laura Sinclair at NIST Boulder. And we had the opportunity a few years ago to actually throw these into action and to do a proof of principle experiment over their 30-kilometer length. So you can see the terminal, it's shown here. And we're sending pulses to this mountain that's shown in the very background of the photo, and they bounce off a mirror and return here. And so this experiment, this optical link, it exhibited coherent phase step-free operation that really supported femtosecond level of time transfer. So in the intervening time, we've been hard at work at further integrating these optical transceivers. And this really led us to our second commercial offering, which we're really proud of. So this is a 9-liter, it's about 1.5U package. This is our current dual comb system. And so this contains 2 frequency combs. They're rep rate matched, obviously. It also includes all of the self-referencing infrastructure, and photo detectors, current sources, temperature controllers. And so you just get your beat notes out of this front panel, and you can lock up your experiment. So we're really excited about the options that this further integration afforded us. And so we went back to NIST this past spring with a goal of combining some of these neat frequency comb transceivers with our iodine optical clocks. And specifically, we want to set up a 3-node optical network that would be located across Boulder. And so 2 of the nodes of this network would be located on the NIST campus, actually co-located in this attic room here. And the 3rd node, which is actually a relay node, would be located about 15 kilometers away at a terminal on Table Mountain. And so you can see this dome with a hatch in it. And so inside of this dome contains the optical terminals that are sending pulses back and forth from this remote site to NIST. And so being able to put our optical clocks and combs into this remote site, this is really enabled by their very low environmental sensitivity. So here's a little more detail as to the actual experiment. So as I said, it's a 3-node network. So 2 of these sites are co-located, site A and B. These are on the NIST campus. So each one of these contains a clock and one of these dual comb sync modules. And then the idea is to compare these across the 30 kilometers via an intermediate relay node. And that relay node consists of yet another iodine optical clock and a dual frequency comb transceiver. So this was parked out at Table Mountain. So this entire assemblage of equipment here consisted of 3 iodine clocks, 7 frequency cones, and 4 optical terminals. And these 2 time transfer links were operated simultaneously in parallel over this 15-kilometer link. So here's a few photographs of the team setting up the 2 co-located nodes on the NIST campus. These are nodes A and B. The clocks and the transceivers are located in this rack here. The light is delivered from this rack over to the terminal. You can see in this left-hand photograph where the light is shot out this window to Table Mountain, 15 kilometers away. All of the discriminators for the timing signals come out of the transceivers. They're processed by these real-time signal processors that are placed on top of the rack, and that converts the optical signals into these nice electronic signals that is used to actually measure the timing uncertainties. So on the other side of the link, site C, so as I said, the terminal itself is placed in this hatched dome. So this contains the 2 optical terminals that are sending and receiving light from the NIST campus. There's this adjoining building that's loosely temperature controlled, and this housed the 3rd optical clock and dual comb system that was acting as the relay node. So this is a photograph from the inside of that dome. You can see the NIST campus in the far distance here. So inside of that little building, this is the iodine optical clock and the dual comb. And so putting this in place, this really got the 2 simultaneous links up and going, and we could begin to see what the data looked like. And a snippet of that is shown here. So these 2 time traces capture the timing error for 1-way and 2-way. So the 1-way, obviously, this blue trace, it exhibits more fluctuations because this is prone to changes in the optical path length between the site A and C. So you can actually remove any sort of common mode fluctuations by taking 2-way data. That's why the orange traces are quieter. And so it's the same story for the BC link. So these orange traces actually reflect the dynamic character of the clocks themselves. And so this experiment ran continuously for about 26 hours. And it was actually only interrupted by a historic snowstorm came into the area and knocked out power to this hutch in the adjoining building. And after, I think it was 4 or 5 hours, the power was still out, and the UPS powering the clock in the dual comb system went down, and that ended the measurement run. So as I said, the initial aim was to actually compare these 2 co-located clocks, A and B, via this intermediate clock, C. And you can do that actually by now subtracting these orange traces. And so in doing so, you can compare A and B over this 30-kilometer link. And that is shown by the blue trace in this curve here. And so one of the reasons why these 2 clocks were co-located at NIST is we can actually compare them directly. We don't have to go over the link. And so this serves as the truth, what these things are actually doing without any contamination from the free space link. And that is actually shown by the blue trace here. And if you squint, you can maybe see the blue behind the orange, but these 2 curves are really superimposed. And so it's showing that this intermediate relay node, which is made possible by an iodine clock, is really very faithfully transferring time between sites A and B across this 30-kilometer free space length. So we can go on to quantify a bit more carefully, how well this works. And so if we compute Allen deviations for the 2 individual lengths, A to C and B to C, so that's shown by this left-hand panel. And so these pretty faithfully reproduce the known laboratory performance for the involved clocks. And so we see short-term instabilities of about 6 parts in 10 to the 14 and 5 parts in 10 to the 14. But then if we look at the Allen deviation, using the difference of the 2 lengths, so the AB measurement, so we do the over-the-air and the local truth measurement, we get these orange and blue curves. And these are now really, again, as we saw in the time trace plot, these are really spot on top of one another. we can go on to analyze the Allen deviation of the residuals, the difference between these two curves, and that is shown by this final right-hand plot. So this is averaging down as white phase noise, and it showed that these two things agreed to, a few parts in 10 to the 17 after 10,000 seconds of averaging. So this was really a great demonstration of the capability of the clocks and the time transfer hardware operating in unison. We were pretty excited about this, and happy to see the creation of really a multi-node optical network. So from here, I'm going to transition into the last portion of the talk. And so we've also been working hard to further simplify the synchronization scheme. So to chip away and remove everything that is not necessary, make some compromises, and still deliver something which is robust and capable of sub-picosecond synchronization. So frequency combs, which we've been using, these things are great. They're amazing instruments, absolutely incredible precision, but there's several drawbacks in using them as a carrier of timing information. So first, there's the actual overhead of needing a second frequency comb. So in addition to the comb, which is already present with the clock. And then there's the role of dispersion. And so these experiments operate in the time domain. So any sort of link dispersion, either in the actual air index itself over appreciably long lengths, or in fiber delivering light from the clocks to the terminals, this spreads out the pulse, and it decreases the precision with which one cone can gate another, and so it decreases the sensitivity. So dispersion compensation is very important, and it makes it difficult to envision actually tracking moving objects through the atmosphere where there's an appreciable changing of the optical pattern. So another subtle technical issue is that there are Nyquist limits associated with frequency comb. This arises from the nice regular spacing of the comb teeth. And so when one target is moving, you can actually create pulse-to-pulse ambiguity issues. It makes it challenging to disentangle the actual timing instability that the one frequency comb is transmitting through the atmosphere. So an alternative to combs, as I said, is to transmit a single CW laser through the atmosphere. And so this is the approach pursued by a number of groups, but the University of Western Australia is really doing phenomenal work toward this end. And they're borrowing a technique of Doppler compensated fiber links, and they're applying it to free space. So the issue with this is that now one optical cycle of their CW laser is 5 femtoseconds. So if there's ever any blackout or fade out of the signal, the clocks can move around by 5 femtoseconds in very short order. And when the signal returns, the fade out disappears, it's difficult to know which fringe the timing comparison was originally sitting on. And so the net result here is it's hard to prevent cycle slips of the time scale during dropouts or fade outs. So we've been trying to take the best of both worlds and develop a hybrid approach where we're combining the group delay provided by the frequency comb with the simplicity afforded by these CW lasers. And so we've been terming this a two-tone approach to optical time transfer. And this cartoon illustrates the basic principles of the technique. So on the left-hand side here, we see this is the traditional frequency comb-based approach to measuring timing error. And so we have a comb at our local site. These are the orange pulses here. And that is measuring the frequency comb received from the remote site. These are the blue pulses. And we're gating, we're interfering the orange and the blue pulses, and the orange gates the blue and measures the jitter of one envelope with respect to the other. So the quantity of interest that we want to extract is this envelope offset, this tau. So of course, we can Fourier transform this picture here, and we can represent it equivalently in the frequency domain. And so we have the nice equidistant frequency comb picture. This corresponds to both of these. And we know that anytime there is a shift of the envelope, this corresponds to a linear spectral phase in the frequency domain. So this orange pulse train has we can say a flat linear spectral phase, and there's a time offset between the blue and the orange. So there is a linear spectral phase for the blue pulses. And the difference of these is directly proportional to the thing that we are interested in, this temporal offset. So one approach is to, rather than measuring this in the time domain, is to do so in the frequency domain. And so as we all know, you can fit a line to 2 points. And so what this means is it's in principle to actually throw away all of these comb teeth except for 2, if we're only interested in the linear spectral phase. And so we can sample the differential spectral phase at 2 discrete frequencies. They're separated by a known spacing. And by measuring the difference in the spectral phase at this spacing, we can reconstruct the thing that we're interested in, this clock jitter, tau. And so we're getting the group delay between these 2 things with only 2 CW lasers. And so one nice advantage to this frequency domain measurement is that you immediately avoid the effects of dispersion. So we don't care about these pulses smearing out in time now. Another way to say this is that fitting this line to 2 points, it's orthogonal to a quadratic contribution, which is arising from dispersion. So how does this work in principle? So this is a block diagram of the apparatus that we've built and set up at Vector Atomic. And so it's a 2-way technique, as before. So each site contains an optical clock that's shown by this upper block, as well as a transceiver. And this transceiver contains 2 CW lasers. And so we use very inexpensive, cheap DFB lasers. And these 2 CW lasers are phase locked to the frequency comb. This transfers the frequency instability of the clock through the comb to these 2 CW lasers. And then these 2 CW lasers are exchanged with the adjacent link, adjacent site over the link. And we end up comparing the local CW light to the remotely received to extract this differential phase. So, and again, this phase difference is directly proportional to the group delay, the transit time between these 2 terminals, plus the clock instabilities. So what's nice is that the sensitivity or dynamic range of the technique, it's determined by the CW laser spacing. So this is adjustable based upon the application. There's no need to worry about the pulse dispersion, since the comb light never leaves the site, it's never transmitted. There's a continuous signal, so we don't have to look for pulse overlap. And then there's no Nyquist frequency anymore. And so Doppler shifts, they lead to change in the beat frequency, but we can follow these so long as the detector bandwidth is large enough. So we recently posted some initial demonstrations of time transfer using this technique to an archive paper. So I would encourage you to check this out if you want further details. So one of the other neat things about this is that it's really amenable to photonic integration. So this is a photograph of the custom PIC that we designed and fabricated. So this is the backbone of the optical transceiver. So all of the beat notes and the referencing of the CW lasers to the cone are achieved on this chip. And so this minimizes any out-of-loop paths, thereby mitigating non-reciprocal effects to really millimeter type of length scales. So presently, we employ pretty cheap DFB lasers, but what's nice about that is you can pretty readily integrate these onto the chip as well, either through a hybrid integration, so coupling them to a chip, or actually integrating them onto the chip itself. So this is something we are looking at pursuing down the road. So how does this work? Well, as an initial demonstration, we set up a free space link of about 100 meters at our facility here in Pleasanton. And so what we wanted to do was to look at the fidelity of just the link itself. So it's the same clock on both sides of these links. And we send out about 100 picowatts of power. And this traverses not only the 100 meters of free space link, but about 100 meters of fiber and getting from the clock actually to the terminals. And so this would be a problem for the cones. We would have to dispersion compensate that. So presently, we don't worry about this at all. And so with 100 picowatts of transmitted power, we're reading a timing resolution of fidelity of about 500 attoseconds with a second of averaging. And this maintains better than a femtosecond out to 10,000 seconds. So we can convert this timing instability to an Allen deviation that's shown in this middle plot here. And we see that the two-tone technique is able to read out clocks at the 10 to the minus 18 level after 1,000 seconds of averaging. So for reference, the green points here illustrate the Allen deviation for our evergreen optical clock. So clearly there's plenty of margin here. We're able to link up multiple assets of the iodine optical clocks, but it's also able to read out kind of state-of-the-art optical lattice and single ion optical clocks. And so this is from a recent publication at NIST. And then finally, we wanted to measure the sensitivity of the technique as a function of the received power, how much light you actually have to get across the link. And so that's captured by this last plot here. And we see that even with just a picowatt of received power, we're still able to measure with a timing resolution of about a femtosecond. So this was pretty encouraging to see. So after doing this common clock measurement of the link itself, we actually wanted to measure two of our clocks across this link. And so these are two of our generation 1 and generation 2 iodine clocks. They exhibit short-term instabilities of about 2 and 5 parts in 10 to the 14. The clock light is transmitted to the optical terminals. There's some fibers in this picture that's sending the clock light out to the transceiver. And we measure these over that free space length over a period of 4 days. And the corresponding TDEV is shown in the middle here. So at short time scales, we see about 20 femtoseconds of jitter between the two clocks. That's captured by this zoom in plot here over an abbreviated time window of 10 seconds. They're moving around at tens of femtoseconds. And over the entire 4-day run, they're bouncing around by not more than plus or minus 600 picoseconds of walk off. And so just to confirm that what we're measuring here agrees with a non-link measurement. So we can convert this TDEV into a fractional frequency Allen deviation, and we show the two-tone measurement in blue, as well as what is obtained with a traditional frequency counter measurement in the red. And so we see good accord here. And so we're pretty excited about these initial results for the two-tone technique, and we're actively working on integrating the system and beginning to take these links outside and start to attack farther and farther distances. So with that, I'm going to conclude. And hopefully I've been able to offer a few examples and demonstrations that illustrate how optical clocks can improve performance in existing timing networks. We're really excited about extending the reach of high performance timing. These evergreen clocks, they're starting to hit the market. We're excited to say we've delivered a few of these alpha units to customers, and can't wait to see what uses our customers are going to dream up for them. Optical time transfer methods, they are also showing really phenomenal levels of timing precision, whether it be over fiber or free space. We can distribute timing at femtosecond levels. And so you can really begin to envision creating picosecond type of timing networks on optical clock bedrocks. And the final point I'll mention is that these technologies are really likely compatible with future space implementations. And so we're starting to actually move in this direction. And our 5-liter clock, which is shown here, we're starting to take an eye toward space and getting this thing on a future satellite. So with that, I'd like to thank the entire Vector Atomic timekeeping team. There's a lot of people behind all of these demos. So it's a great team. Fantastic colleagues that I get to work with every day. We've had something like 30 plus clock demos to date, and more are on the radar. So stay tuned. And then finally, I'd like to thank our collaborators, specifically at NIST Boulder in this 3-node networking experiment, and then also at the University of Arizona and Harvard for this VLBI experiment. And then finally, our government sponsors who have really made all of this possible through their generous funding. So with that, I'll conclude.
Wonderful. Thank you very much. All right, let's open the floor for questions. Sure. All right, maybe I can have the icebreaker. So
Sure.
How are you seeing, like, let's say, the miniaturization of these products?
Yeah, so let's see. So this actually isn't a cartoon. This is a CAD rendering of something we're building right now. So this is a 5-liter version of the Evergreen clock.
Mm-hmm.
And this is something we're actively hard at work at. And we think we can basically put the Evergreen inside of this box without compromising on the performance. And so that's something which is exciting. So we're also actively working on a much more aggressive reduction in swap. And so I mentioned earlier a 1-liter clock. And so this is not as high of performance as the Evergreen or this 5-liter clock. And so giving up on performance, we're able to cut some corners in the spectroscopy and in the laser, the electronics, the frequency comb. And so it's we're trying to be smart about these corners that we're cutting and still deliver a really attractive product offering probably a few parts in 10 to the 13 stability on a 1-liter package.
I find this first. In general, this is just the expression used. Like it's very funny when we use liter for like these equipments. While I just went through a water damage from my lab, but, but when are we getting to, let's say, milliliters?
Yeah, so that's okay. So now you're talking about really aggressive
yeah, like CSAC
integration. So
like
CSAC,
that level, yeah.
Yeah. So we have, I wouldn't quite say milliliters, but we have on our roadmap some even more aggressive integrated products that we're starting to look into. And so this really involves very micro spectrometers and frequency combs. So I think it's probably a fair statement to say that the more corners that we cut and reducing the swapcy of these things, we're going to start to take a hit in performance.
Yes, of course.
But some paper studies that we've done with these sub-liter clocks, we still think we can deliver something attractive, take advantage of an optical flywheel, and deliver something probably quite a bit better than at least the CSAC specs that I'm aware of. So of course that's going to be further down the road, and so I think we're hoping to have this 5-liter version in a 2-year time scale, and then the 1-liter version maybe 2 years after that, and by that time we'll probably be hammering away on your dream of a
wonderful
milliliter type of device.
Wonderful. All right, let's open the floor for questions. Yeah, Hisham?
Sorry. Question.
We go Hisham first, then we go Andres, then we go Juan.
Sure. Very good presentation, excellent presentation, Jonathan.
Oh, thank you.
But when Tara and other people from NIST came to present to the OCB tab community about time synchronization in quantum networks, they highlighted some of the outstanding challenging problems that still need to be addressed. So from your perspective, what problem you still think need to be solved and requires research and to be addressed by the community?
Yeah. Okay. Yeah. Thank you for the question. So, so regarding kind of, if we look at the current state of affairs for optical synchronization, what are the existing roadblocks? So I would probably really defer you to Emily Caldwell's talk a few months ago. Her and her colleagues at NIST, are really the experts on this, and so I don't want to speak out of turn. So I think the comb-based approach is, it's really quite well developed, and it's achieving great results presently. I think if you were to ask those people, they would say that the next thing that they're the next issue that they're working on is motion, and so these problems associated with Doppler shifts, and when the individual lines of the cone begin to alias into one another. And so actually, if you crunch some numbers, the current limits on motion are, I think maybe tens of meters or 100 meters per second before you begin to run into this pulse-to-pulse ambiguities. And so, certainly if you want to envision doing transfer to LEO satellites, you need to be able to accommodate kilometers per second velocities. And so I think this is something that they're hard at work at attacking.
Oh, thank you.
All right, Andres.
Yes, so I have sort of a follow-up question to what Ahmad mentioned on miniaturization. So what are some of the, can you speak a little bit to the challenges in terms of components? What are the components that, because I know system integration is a whole thing, but there's a lot of problems in supply chain of components and miniaturization of individual components. So what are the sort of key elements that need more research into miniaturizing clocks like this? And sort of adjacent to that, you mentioned miniaturizing would take a hit, your systems would take a hit in performance, which that makes sense, of course, but I'm also wondering if there is maybe any commercial markets or any markets that, don't need the femtosecond level synchronization, but would benefit from whatever the performance hit is if you miniaturized, if you lower the cost. So yeah, so two parts: what the components, and then can you foresee any sort of market adoption for lower performance clocks?
Yeah, sure. Thank you for the question. So regarding the components, so all of these systems, so whether it's the 30 liter, the 5 liter, the 1 liter, they have three main components. And so there's the spectrometer, so where we are interrogating the atoms. There's the laser system, and then there is the frequency comb. And so you can say electronics is a fourth piece of the pie as well. But actually, in order to beat back the swap of these systems, and so we don't really consider electronics as a separate entity right now. And so electronics for the relevant subsystems is really integrated into the subsystems themselves. And so when you speak of components, I guess we're talking about these three things. And so, we're hard at work at aggressively integrating and reducing the swap of all three of these components. Example is, that current generation of the frequency comb. So that's now 0.1 liters. And so this is, still a comb capable of reading out a clock a few parts in 10 to the 17 at a second. And so this is required a lot of creativity and understanding what corners we can cut and compromises we can make in order to beat back swap of these systems while maintaining performance. Regarding the potential market, we think of course there's a very large potential market who is eager to get their hands on an upgrade in timing infrastructure. This 1 liter system that I mentioned that we are working on. So right now, this is delivering a part in 10 to the 13 instability at a second. So it's not as good as, you know, the evergreens and your femtosecond precision, but it's still exceeding. It's certainly exceeding what RAFs can do, and it has the you know, so far you know, it's looking pretty attractive at longer time scales, and, you know, holding about a part in 10 to the 14 at daytime scales. And so, you know, it's really kind of hoping to compete with a cesium type of application. And so, you know, of course, the smaller and cheaper that you make these things, you know, the more adopters you're going to have, and the more application space you're going to have access to. I don't know if that is addressing your question.
Yes, thank you very much.
Yeah, thank you.
All right, Juan was next, and we go for Laura after that.
Hello, I just joined to the meeting. In this moment I don't have a question or comment
No
for
problem.
anything.
No
Thank you.
problem. Thanks. Laura?
Yeah, I hope you can hear me. I have a very bad cold today.
Here.
Okay. Thank you very much for this very nice talk. I was very impressed by the video you showed when you showed like the starting procedure of the clock, of the iodine clock.
Yeah.
As far as I know, there are like 10 transitions of the molecular iodine you can lock to. Do you lock every time to the same transition, or can you vary, or how do you know which transition you're locking to?
It's a great question. So, so you're right. So one of the neat features of a molecule is that there's a number of different transitions you can lock to, different row vibrational transitions, and then even within a given hyperfine manifold, depends upon which manifold you're in, whether it's 15 or 21. And so, you know, how do you always lock to the right one? And so, you know, the short answer is, you know, we developed some algorithms. Generally speaking, unless customers, I think, demand otherwise, we're locking to the central peak. It's denoted A10. It's probably the most common iodine line in the literature. And so these algorithms identified A10 and always lock there. We've had some requests and some interest in the capability to lock on other lines. You know, people have asked about A1 and A15 for the real connoisseurs out there. And so the software team, I think they're hard at work in kind of updating these algorithms to allow the customer to switch lines if they want to.
Yeah, thank you.
Yeah, thank you.
Wonderful. Any more questions? All right. If no more questions, we'll see everyone in 2 weeks. And we want to thank again Jonathan for his great presentation. And as always, like, the recording will be available on the website alongside with the slides after Jonathan sends them to me.
Yeah, well, thank you again.
Yeah. Thank you, everyone.
Thank you all for attending.
Thanks. All right. Bye, everyone.
Bye-bye. Cheers.
Bye, everyone.